scuseremo chi arriva in ritardo per questo problema. Sono 28 anni sono trascorsi da quando abbiamo assistito e registrato la prima intensa fioritura algale nel lago di Serraia. Nonostante gli interventi che sono stati realizzati per fare il risanamento dello stato eutrofico, purtroppo il livello di fosforo totale, che è l'elemento critico che determina la proliferazione algale, non è diminuito in maniera significativa. Tant'è vero che le proliferazioni algali si sono poi manifestate anno dopo anno con l'aggravamento del fatto che sono intervenute delle nuove specie, diciamo batteri, che hanno la particolarità di produrre delle tossine, quindi il problema si è ulteriormente aggravato. In quel lontano 1997 il Consiglio Comunale, prendendo atto della situazione del lago, esprimeva tutta la sua propria angoscia e la preoccupazione per il futuro del lago, citando una nota canzone della Beppe De Marzi, "L'acqua s'è morta". Ebbene, a 30 anni di distanza non possiamo parlare di una Pasqua di risurrezione per le acque del Serraia. Il fatto che dopo così 30 anni non si sia riusciti ad avere un minimo miglioramento delle condizioni del lago sta a significare che le misure messe in atto o erano e sono inadeguate o non sono sufficientemente efficaci per raggiungere lo scopo che si prefiggeva. Buon pomeriggio, io sono Claudio Ioriatti e da maggio ho l'onore di presiedere il comitato Laghi, tutela laghi di Serraia, piazze relativi ecosistemi. Ho rilevato il testimone dal professor Mattivi, che ha guidato il comitato nei primi 3 anni, contribuendo in maniera determinante al conseguimento dell'importante riconoscimento che è stato riservato al comitato Laghi da parte di Legambiente, la bandiera verde. A questo proposito vi invito tutti quanti al termine della conferenza a un brindisi per festeggiare questo importante riconoscimento, che per noi è gratificazione per il lavoro fatto, ma è anche stimolo per continuare il nostro impegno per la salvaguardia dell'ambiente pinetano. Il Comitato Laghi è stato fondato nel 2021 da un gruppo di cittadini, in parte residenti, in parte frequentatori dell'altopiano. Attualmente conta oltre 100 soci, molti dei quali vantano esperienza e competenze dirette in temi ambientali. Ed infatti l'obiettivo del comitato, constatando questa inerzia e questa difficoltà a conseguire dei risultati in 30 anni di cui ci si occupa del lago, ha pensato di mettere in campo le proprie competenze, condividere le proprie competenze per indicare, trovare e suggerire degli nuovi indirizzi per poter arrivare a arrestare questo costante degrado della qualità del lago di Serraia, o perlomeno magari anche invertendo il processo. Il compito, gli obiettivi che il Comitato Laghi si è dato sono numerosi, ma fra questi c'è anche proprio il fatto di proporre dei momenti delle conferenze, dei momenti di condivisione della conoscenza, stimolare la collaborazione con enti e istituzioni al fine di raggiungere appunto la salvaguardia dell'ambiente laghi e ambiente pinetano. In questo senso appunto si colloca la giornata che stiamo proponendo a voi presenti. Abbiamo invitato per questo 3 fra i principali esperti in campo internazionale relativamente al risanamento dei laghi eutrofici. Sono 3 persone, 3 ricercatori, tuttora molto impegnati, nello sviluppo di approcci innovativi per la valutazione e la gestione del carico di nutrienti e per la valutazione dei rischi tossicologici legati alla presenza dei cianobatteri. Lascerò al professor Mattivi e al professor della Volpe, moderatori della giornata, la presentazione dei relatori. Io mi limito a esprimere il ringraziamento di noi tutti soci per aver accettato l'invito a essere qui oggi a condividere la loro esperienza, le loro conoscenze, che sono di gran lunga che sono veramente importanti per suggerire delle nuove strade a chi deve prendere delle decisioni in questo campo a livello locale. Nell'ambito dei ringraziamenti ovviamente corre l'obbligo di ringraziare chi è stato al nostro fianco nell'organizzare questo momento di informazione, in primo luogo la banca Trentino Südtirol che ci ospita, indubbiamente il comune di Baselga di Pinè e la Cassa Rurale Alta Vassurana che sono al nostro fianco nella promozione e nell'organizzazione della rassegna estiva Il Respiro dei Laghi, arrivata quest'anno alla sua terza edizione, nell'ambito della quale si inserisce anche questo evento. Metafin Italia, che è un leader internazionale nella gestione delle acque a fini irrigui, ma molto spesso frequente a supporto di progetti di sostenibilità. Infine, come accademico del Georgofili, sono particolarmente contento che l'Accademia abbia dato il suo patrocinio a questa iniziativa, un sigillo di scientificità qualora ne fosse stato necessario. Ricordo che l'Accademia dei Georgofili è la più antica istituzione al mondo che si occupa di temi legati all'agricoltura, all'ambiente e all'alimentazione, al fine di far progredire dal punto di vista tecnologico, economico e creare aumento degli aspetti sociali. Purtroppo il presidente della sezione nord-est, che avrebbe dovuto intervenire questo pomeriggio, ha avuto dei problemi, quindi mi ha incaricato di porgere il saluto suo e dei membri dell'Accademia a tutti gli intervenuti, in particolare appunto ai relatori. Bene, prima di dare la parola al sindaco di Baselga, voglio di nuovo rinnovare il ringraziamento per la vostra presenza. Sono sicuro che sarà un pomeriggio importante per la formazione e per l'ispirazione di nuove linee di ricerca e di applicazione. Grazie di essere intervenuti.
Bene, buonasera a tutti, un grazie e un benvenuto ai relatori di fama internazionale che ci portano ulteriore conoscenza per cercare di affrontare ancora in modo più completo e risolvere, speriamo in tempi ragionevoli, il problema del nostro lago. Voglio ringraziare il comitato che, come giustamente ricordava il neopresidente ed ex sindaco, quindi ha omesso che in quegli anni era lui il sindaco di Baselga di Pinè, quindi la vicinanza al lago, che è la perla dell'altopiano, è condivisa da molti cittadini e non solo, spesso da persone fuori dal nostro territorio è ancora più apprezzata. Come amministrazione abbiamo subito preso in carico questo grosso problema e con il comitato al nostro fianco veramente è stato fatto un importante passo avanti su tanti fronti. Abbiamo qui, e ringrazio anche la progettista appunto di un importante intervento di riqualificazione dell'area attigua al lago. Sono state messe in campo importanti iniziative, importanti risorse per migliorare la qualità delle acque. Speriamo che anche dall'incontro di oggi, che abbiamo già anticipato magari stamattina a mezzogiorno, escano delle ulteriori input e informazioni per affrontare ancora in modo più completo questa complessa problematica che necessita chiaramente di un approccio come dire, a 360 gradi. Quindi un grazie ancora al comitato, un grazie ai relatori per aver accettato l'invito e buona prosecuzione a tutti. Grazie.
Okay, while they are preparing the presentation, just a few words about the first speaker, Dr. Ingrid Chorus. Until 2019, she was head of the drinking water and pollution department of the German Environment Agency. So this means that she had a very important role of responsibility in the field of drinking water for the whole Germany. And her research interests include limnology, especially phytoplankton ecology, toxic cyanobacteria, and eutrophication control. Their further interests include the impact of water on public health, in particular attenuation of pathogens and hazardous substances in the aquatic environment. Her presence today is particularly relevant as she can illustrate her experience in combating and preventing cyanobacterial blooms, managing the threat to humans and animals caused by cyanotoxins, and decades of study of the restoration process of a eutrophic lake. So this is also a common point on the speaker today. They were investigating for 20 or more years process of restoration of lakes in Germany, in Netherlands, mainly, and not only. And so they already can share with us the experience of a process which is for Lake Serraia is starting now. Now we are at the point that the municipality and the province is putting in place several studies and now the choice of what to do. They were already going through this process for the last at least 20 years, so they can say what can work, what can work less, and what will never work. Because there are also a lot of commercial proposals which are promoted, sold, and several of them are totally ineffective. So the point is only also to do a very careful examination of each specific body system to find out what can work in that specific case. There is not a golden bullet which will fix everything. It does not exist. There is not a single action to be done, and the actions are not the same for different lakes. So this is the expectation we have today. Just a second, because it seems we have a problem with the presentation.
Wow.
Okay.
Okay, thank you very much. Grazie to the Comitato for inviting me. We had a beautiful day today with perfect weather, walking around Lake Serraia and looking at it and trying to understand what makes this lake special. I will try to go into how much cyanobacterial biomass is dangerous for health, how much is safe, to give you some background to discuss the targets that are needed to be achieved to make sure that people are not exposed to dangerous concentrations of toxins from cyanobacteria. The amount of biomass that is safe translates into amount of phosphorus. Phosphorus fertilizes the growth of the cyanobacteria, like plants. And I want to show you some international experience with the restoration of lakes, as well as experience in Berlin, like Claudio already said, and conclude with a few other considerations. Now, how much toxin does biomass contain? With the World Health Organization, with whom I was involved in developing the guidelines for cyanobacterial toxins in water, we looked at data from a number of water bodies to estimate what's the worst case ratio of toxin to biomass. And this graph here shows you data from a number of lakes. And the worst case situation is about 3 micrograms of toxin per cubic millimeter of what we call biovolume. Now, the way to measure biomass of cyanobacteria is to look at them in the microscope and then to measure the linear dimensions. So if something is cylindrical, you measure the diameter and the height, and you use the geometry that you learn in school for the average volume of a cell, and you multiply that by the number of cells per milliliter of water. And that gives you a measure of the cell volume, the biovolume in the water body, which is what we use as a proxy for mass. So what we can see from the experience that is shown with these examples is that we can expect 1 to 3 micrograms of this toxin per cubic millimeter of biomass of cyanobacteria. Very often it's less. This is a worst case approach. That's important to remember. In many, many cases, it's a tenth of that. If I'm too fast for the interpretation, let me know. So the World Health Organization derived these guideline concentrations for microcystins and other cyanobacterial toxins in drinking water, differentiating by the concentration that is safe for lifetime daily consumption of 2 liters of water, but also looking at extreme events in some situations where you have a bloom only for 2 weeks or so. The water company needs a bit of time to adjust the treatment, and the 12 micrograms here for a short-term exposure were meant for such situations, and they are still safe. For recreational exposure, it's 24 micrograms, and for other toxins, there are different values. They're all based on animal experiments, and I'll explain how these work. What is normally done is that a group of mice is exposed to certain dose groups where they get the toxin in their drinking water every day. And you look at the dose that has only a minor effect and the dose that has no observed adverse effect. And we will now look at these a little bit more closely. So what was seen for microcystins was a dose with a clear effect with 1,000 micrograms per kilogram of mouse weight, a dose with minor effects, and a dose where they saw no effects after many weeks of daily exposure to this toxin. This is called the no observed adverse effect level. That then was 40 micrograms per kilogram. Now to derive the guideline value, this gets divided by a factor of 10 to account for the differences in sensitivity between species, and another factor of 10 for differences in sensitivity within a species. And we know this from pharmacology. Some people respond a lot more to a drug than others. There are differences. And then, of course, there are some uncertainties in the data. These mice were not exposed for a full life cycle, but just for about 2/3 of it. So there's another factor of 10 for this uncertainty. So altogether, to estimate the total tolerable daily intake, the NOAL gets divided by 1,000. I think this is really important to understand. The little red cube in this top left corner is to visualize how low the tolerable daily intake, the TDI, is in relation to a dose that already did not cause any observable harm. So if you're exposed to this TDI, that is quite likely to be safe. Now, how does that convert to the concentration in water? You use the NOAA and relate it to the average body weight of a person per day and the consumption per day, and you use a partitioning factor, in this case of 0.8, to allow for some exposure not only through drinking water, but for example also through recreation. And that then multiplies this NOAL of 0.04 micrograms per kilogram body weight with a factor of 60 kilos and 0.8 and divides it by 2 for the assumption of 2 liters of water per day. And the outcome is 1 microgram per liter of drinking water. For short-term exposure, where a bloom occurs in the reservoir only for a short time, you don't necessarily need this uncertainty factor for lifetime, so you leave out a factor of 10 And you use the partitioning factor of 1 because in that situation, drinking water would be the main exposure route. And that's how you arrive at the 12 micrograms per liter. That would be allowable for 2 weeks at most. And for a recreational exposure, the assumptions are a little bit different. The worst case assumption for a child of 15 kilos is that it would swallow 250 milliliters of water in a recreational event. So a bit more than a glassful. Quite a lot for a small child. And that gets you to the 24 micrograms per liter if you do the calculations. So the message here to take home is to remember that if you find a few micrograms more than these values, it is still very unlikely to be dangerous. It's still very much in a safe zone. Quite often we find that people are very worried if the concentrations found are a little bit above the guideline values. But if you understand how they are derived, you know that that is not yet dangerous. Still, if you have microsystence in the milligram range, in the pea soup consistency, it's a different story, and we do want to protect people from that kind of exposure. Now, how much toxin does the biovolume contain? Oops, I already explained that, okay. Now, how do we ensure that the biovolume target that we have of 8 cubic millimeters per liter of water is not exceeded? It's not only for human health, it's also for keeping a water body attractive. If you look at this picture, don't need to say much, right? It's clear that it's not attractive. It makes beautiful patterns for artists, but it's not what you want to swim in. So, why do we address phosphorus? Cyanobacteria, like all life, are chiefly made of carbon, of water, of course, of nitrogen and phosphorus. And water is unlimited in their environment. Carbon enters the water through the air, carbon dioxide. Concentrations of nitrogen and phosphorus enter water through sewage, through manure, through fertilizer, and that can be controlled. Addressing nitrogen can work. There are very few examples around the world where nitrogen was reduced to concentrations so low that we did not see blooms anymore, that they disappeared. Lake Lürling is one example where it was by coincidence because the agriculture and the catchment collapsed after the political changes in the early 90s. But we don't have much experience with reducing nitrogen sufficiently, partially because nitrogen fertilizer is cheap and easy to use, and partially because it's a little bit more challenging to remove that in sewage treatment. But reducing phosphorus has worked very well, and there's plenty of experience. Just 4 lakes to show you examples. Lake Constance, the peri-alpine lake in southern Germany, Switzerland. It has, well, first of all, I need to explain these graphs. The total phosphorus concentrations on these graphs are the squares. Chlorophyll A is used as a measure of biomass of all of the phytoplankton, all of the algae and the cyanobacteria in the water. They all contain this green pigment that we all know from plants, chlorophyll, and it can be used as a proxy for biomass, and it's very commonly used because it's easy to measure. And we plotted the cyanobacterial biovolume, and we see 2 things in these graphs. These little red circles that I'm just showing here show you that sometimes the ratio of chlorophyll A is about 1 to 1, 1 microgram chlorophyll per microgram phosphorus. And these are the bloom situations where all of the plankton, the phytoplankton in the water, is cyanobacteria, where you have hardly any other algae. The bars show you the biovolume of the cyanobacteria, and the triangles show you this proxy for all of the phytoplankton. And what we really see is how far we have to go down with the total phosphorus concentration for these bars to get smaller, for the cyanobacteria to be a lot less. And in Schlachtensee, we even went down further with the total phosphorus, and we see a further decrease decrease. You might not be able to see it on the screen if you're sitting in the back, but these little tiny bars in the bottom are almost invisible now, so there's almost no cyanobacteria anymore. We also looked at the data from 17 different lakes across Europe and North America, and we plotted chlorophyll against total phosphorus, and we connected these chronologically, and I think I need to explain this. This is where we had, before we started restoration, this is the concentrations we had before we started restorations, and we used the average, the summer average of each year and plotted this consecutively, and you can see that phosphorus declined. This is a log scale over more than an order of magnitude before the algae noticed any difference. And it was only here all of a sudden that we saw a pronounced decrease. So this shows you that, it shows you how far you have to decrease the phosphorus concentration to have an effect. And it also shows you that for large stratifying lakes, you get less, you just don't get these very high phosphorus concentrations. It takes much longer for them to accumulate that much of the phosphorus that comes in from the catchment. And the shallow lakes, they have more phosphorus, but also accordingly more phytoplankton biomass. And one factor that's really important here is that if a lake is mixed very deeply, like these peri-alpine lakes where mixing even in summer goes down to 20 meters or so, and all of this is mixed, if you then imagine a pea soup consistency of the water, that would mean that the cells that move around up and down hardly see any light, because below 2 meters it's dark. So a deeply mixed lake cannot support quite as high a biomass as a shallow lake can. So understanding the depth of mixing is quite important to understand how much biomass you can expect. So I suppose you would like to know where Lake Serraia might fit into this, how low you would have to go to mitigate the cyanobacterial biomass. So let's look at the cyanobacterial biovolume data that we have, and they show, again, as means from May to October, and on that side on a logarithmic scale, and we magnified the low concentration ranges for the lakes without a logarithmic scale on the left-hand side. And it shows you that for a mean biovolume of 8 cubic millimeters per liter, phosphorus has to be below 20 to 30 micrograms per liter. So this is how you can translate the target of toxins into a target of biovolume into a target of phosphorus concentration. But it also shows you quite a scatter of these data, so it really depends a lot on the water body. There are other factors like mixing depth that have a strong impact here on how well the phytoplankton and the cyanobacteria can utilize the phosphorus. So again, to compare Lake Serraia, this time to our experience in Berlin, we have 2 lakes in Berlin, Schlachtensee and Lake Tegel. They aren't at the elevation of Lake Serraia. They're at 30 meters above sea level, so the way they experience the sun is different. I suspect that the amount of sunlight can be quite strong in Lake Serraia. That might make a difference whether within the scatter of data, Lake Serraia would be more on the upper end. But there is some similarity in depth of mixing, and that can be used to compare. The restoration method that was used here was that at the main inflow of these lakes, here, both lakes have one chief inflow, and they put a type of almost sewage treatment plant there that precipitates phosphorus and filters also. Precipitating phosphorus is common in sewage treatment, but usually the water does not get filtered, and that means that the fine flocks that contain the phosphorus are still in the effluent. But if you filter that water, you can get the effluent down to 10 to 20 micrograms per liter of total phosphorus. And this water exchanged the water in the lake within a few years. And what we saw is a strong, not only reduction of the biovolume of cyanobacteria, but also a change in species composition. These graphs show you the biovolume of the different groups of algae. The blue, of course, is the blue-green algae, the cyanobacteria, and they're stacked on top of each other. So what you can see is 1989, 1998, we had other algae in Schlachtensee. The yellow is, for example, for diatoms, which are typical for spring. There's a bit of green here for green algae. And there's a little bit of blue left in 1998. There were a little bit of cyanobacteria, but of course, if you compare the graphs, not nearly as much. And one mechanism that works there is that the species of cyanobacteria that was dominating here, Planktotryx agardii, it doesn't have a lot of loss. The zooplankton don't like to eat it, and it has gas vacuoles that keep it suspended in the water so it does not sediment. So once you have a mass development, it can grow faster than the other taxa. That's the third thing. If it's very turbid, if you already have a lot, and that renders the water very turbid, the other species don't have much of a chance. They're sort of the shade-adapted ones. So once you have them as a bloom, they stay, and sometimes even overwinter. Whereas once you manage to crack that cycle, because you get your biomass down low enough that the water is more clear, the other species then can grow faster, and they can outcompete this Planktotryx, and other species have more loss rates. They are eaten by zooplankton. The diatoms are quite heavy. If the water stops mixing, they sink to the bottom. So they have losses, and that supports getting the biomass yet lower. So cracking this cycle of continuous bloom is important. So to look at the curves for Schlachtensee and Lake Tegel over time that I already showed you in the 17 lakes graph, here they are again. And they're also there with cyanobacterial biomass. And if we think about Lake Serraia, maybe this is about where it could be on, let me show it here. This is about where it is now, and this is maybe where you would want to have it. With more sunshine at 970 meters elevation, maybe the whole thing would move a little bit over here. That would remain to be seen, but this could give you about an idea of where we need to go with the phosphorus concentration. There's another aspect that I want to go into. It's the sediments, the role of sediments. When restoration started at Schlachtensee, people were critical and said, there's so much phosphorus in this sediment, that will never work. The red curve shows the calculated dilution rate with this low phosphorus water, and the black curves show you what was measured. And actually, the phosphorus concentration did go down very quickly, and the sediments were not so much of a problem. But this lake is quite funnel-shaped, so the phosphorus that settles into the bottom layer stays there pretty well. Lake Tegel was different. We had a lot more problems with phosphorus peaks, especially when the phosphorus that accumulates in the bottom layers of the water, in winter when the whole water body gets mixed, it gets mixed up into the whole water body. So we had a lot of work done about how to control that. And one aspect was aeration. And again, I think I need to explain these plots a bit. This is the concentration of phosphorus in the layer above 8 meters. And this is just plotting that's upside down for the bottom layer between 8 and 15 meters, just to show the difference. And this is what accumulates during the summer when algae settle to the bottom, when zooplankton, feces, and dead animals settle to the bottom. That carries a lot of phosphorus to the bottom. The idea with aeration was that if the sediments are anoxic, phosphorus gets released from the sediments, and that's also the logic of aeration in Lake Serraia. But the problem was with a lot of aeration here, it mixed too much water into the upper layers, and we got too much of this phosphorus moved up. So what they did later on was switch on the aeration only in late summer when the sediment started being anoxic. That improved the situation somewhat, but the big question was always, is actually the redox situation at the sediment the problem or not? And if we compare here the total phosphorus concentration in the water right above the sediment and the concentration of nitrate, which nitrate, the molecule has a lot of oxygen, you can already see it in the equation, right? And nitrate is a way to oxidize the sediment surface, and at the time we had a professor, in Berlin, who liked that as a restoration approach, and actually in Sweden tried it on a lake to put in nitrate on purpose to oxidize the sediment. So you could argue it doesn't really matter whether you use ozone or aeration or nitrate, we're talking about oxidizing the sediment surface. So we had a big discussion in Berlin whether we should take the nitrate out of the sewage or be happy that we have it because it might be oxidizing the sediment surface. When we look at this in detail though, we realize we need to be below 0.5 milligrams of nitrate. We need to be above that for desorption of phosphorus not to occur in the sediment, but only some of the peaks of phosphorus in the bottom layer could be explained by very low nitrate concentrations. We had other situations where either the nitrate concentration was very low, like in 1994, but where we had no release, but we had a number of peaks where the nitrate concentration would have been high enough. So we weren't so sure that this was really the main mechanism. So instead we looked at temperature in relation to these peaks. And we saw that we can explain a lot more of these peaks of phosphorus in the sediment with temperature, which was a strong indicator that mixing with aeration makes the water on the bottom warmer, and that leads to mineralization, to decomposition of the organic material there, which also releases the phosphorus that's contained in the organic matter. So the main mechanism might not even have been a lack of oxygen on the sediment surface, but rather if you enhance decomposition of organic material by adding air and warmth, you get a lot of faster decay, and that releases phosphorus again. So we weren't so sure that aeration is really the best idea, and it seemed to be that temperature and mixing was more relevant actually than than anaerobic release. And if we look at the days of aeration marked with these X's here, and the temperature with the triangles, we see quite opposing patterns. Every time aeration was short, every time we had a lot of aeration, we had much higher temperatures and we had more phosphorus release. So to sum this up, how low to go with phosphorus with the Berlin experience, we started looking for microcystins only in 1995. We were not aware of this problem before then, and we did not have the methods to measure. So we don't have any data for the early years where we had the heavy blooms, these blue-green peaks. But what we do see is that at TP below 20 micrograms, we scarcely had cyanobacteria. We had very low concentrations of microcystins, less than 1 microgram per liter, which would be okay for drinking water, less than that, with only one exception in each lake where it went up to 3 and up to 5, if we managed to keep biovolume below 10 cubic millimeters per liter. This is a summary graph showing total phosphorus, total phytoplankton in terms of chlorophyll, cyanobacterial biovolume, and transparency. And you can see transparency increased hugely in Lake Tegel. We used to have transparency measured with a disc that you lower into the water of less than half a meter in summer, and now we are at 8 meters, 4 to 8 meters. It's really now a beautifully clear lake. Now, to finish with other considerations, there's a lot of discussion about how climate change is likely to promote cyanobacterial blooms, although there are also some indications of situations in which they might be less. So let's look at the impacts of climate change, and one is that the duration of the season in which the water body stratifies thermally is longer. It gets warmer in spring earlier and it gets colder later, so you have a couple of weeks more in which the water body is thermally stratified, which is good for cyanobacteria that can that can regulate their buoyancy, and they can move up and down in the water to find nutrients near the bottom and light near the top, and have an advantage against algae that cannot do that. So stable stratification promotes many cyanobacteria, especially microcystis. Climate warming has an impact on nutrient concentrations, not because we know that there's more frequency of storms. Now that can go both ways. It can cause dilution. If the stormwater has less phosphorus than the lake, it can also add phosphorus and nitrogen if runoff from the catchment contains a lot of fertilizer or manure. So it really depends on your situation which way climate change works. It can cause less release or less resuspension of phosphorus from the sediments if stratification is very stable. But if storms are strong and you have them more often, it could also cause more resuspension. So again, it depends very much on your specific lake and your specific situation. The hydrological conditions I already explained, stratification and mixing, that really changes the conditions for scum formation, for the vertical migration, and in some alpine lakes you also have these layers of reddish cyanobacterium, Planktotryx rubescens, which occupies the layer between the warm upper layer and the cold lower layer. So the impact of climate change on the hydrological conditions is really important, and the impact on the water exchange rate as well, and the time patterns of water exchange. There is some direct impact on growth of cells. All cells divide faster in warmer water, but cyanobacteria tend to grow more slowly in colder water, but they have a higher temperature optimum than many other algae. So there is a compensation point where above 20-25 degrees, cyanobacteria can still multiply and survive, and other algae cannot. So there is also this direct effect. Personally, I think it's probably the least important of these. I think the indirect effects are the most important ones. But the message is that there are definitely changes in the risk for blooms. And the big blue arrow shows that it's more likely that they are going to make blooms worse than that they're going to make better. But again, the message is it depends very much on your specific lake and its conditions. Either way, reducing the nutrient load is the most effective measure we can take. It's the thing we can do to strengthen the resilience of a water body against these effects. Now, if you want some more information, there's this book that we developed with the World Health Organization. If you Google toxic cyanobacteria in water, it's free. You can download it for free. And it puts cyanobacterial toxins into the context of other hazards that occur in water, and I think that's important, not to be forgotten, where you get a lot of even treated sewage into a water body. People tend to think treatment takes out pathogens. It reduces them, but there's still quite a lot. We have a site in Berlin where half of the river water in summer is treated sewage. So it really depends on how long that water has been in the river for the pathogens to die. Some of them die quite fast. Viruses don't. They tend to last longer. So there are other reasons people get sick. We see quite a number of publications that claim people got sick from cyanobacteria. Because of the coincidence, people got sick from when they were out swimming or surfing, having a lot of water and swallowing it, And there were cyanobacterial blooms, but what we also can imagine is that a water body that has a lot of nutrients and a lot of cyanobacterial blooms has other things as well, and often it is treated sewage or it's manure runoff from fields. And the symptoms that people describe are much more like infectious disease. It's not the liver failure that you would expect from microcystins. So correlation, coincidence doesn't tell you what's the cause. So you have to be a bit careful with that kind of a report. And colleagues do tell us that when there are press releases out to be careful with cyanobacterial blooms in the lake, the health authorities get a lot of phone calls the day after. So it's the awareness of people, if they have some symptoms, they think it was because of the bloom. But it's not that likely to be correct. This book also gives you some guidance on what to do and how to assess the water body's likelihood to support blooms, here in relation to total phosphorus. With total nitrogen, one could do the same thing, but there aren't enough field data to give that kind of guidance. It also goes into hydrological conditions, stratification, shallow and well mixed. As one extreme, mountain streams or brooks or rivers with rapid flow that don't have cyanobacteria because the conditions aren't that good for them there. And it looks at transparency and pH not as a cause of a bloom, but as a condition that makes it more likely for them to occur. So if you're interested in finding out some overview type guidance, Google toxic cyanobacteria in water. Now to conclude, I'd like to close this talk with the advice that is a conclusion from what I tried to explain about the toxicity in the beginning and about how guideline values are derived. Microcystins don't pass through your skin. To have a problem, you need to swallow them. So don't panic, enjoy Lake Serraia, and you can check yourself. Wade carefully into the water up to your knees, don't stir up the sediment. And if you can still see your feet, swimming is okay. If you can't, check if you can go somewhere else. And sometimes you have the bloom only in a part of the lake, and it's no big problem to find a beach 10 minutes down the path. Avoid ingestion. If you like water skiing, think about the spray that you might get into your face. Be careful not to get too much into your digestive system. And take care of your kids. Kids like to romp around in the shallow water where the scums can accumulate. They show you how they can do a handstand underwater and that kind of thing. If there is visible this greenish discoloration, that's not the thing to do. Go ahead and swim, but keep your head above the water. So, thinking about the future of Lake Serraia, to keep it healthy and attractive, the target should be to get phosphorus down to, total phosphorus down to 20 micrograms or even less by mitigating external loading. And that's really critical. Any internal measure, and I'm sure my colleagues will be telling you a bit more about that, any internal measures that you do in the lake are like putting a Band-Aid on a wound, or even not quite like that because the wound will heal. It doesn't fix the problem if the phosphorus keeps on coming in. It doesn't fix it in the long term. The other message is it takes time for phosphorus to gradually be flushed out of the lake and the phytoplankton composition of species to change so that you have a response to reducing loads. Expect that to take a decade or two, and tell people that so that people will not call you and say, hey, Mr. Mayor, I thought you cleaned up this lake. Why am I still swimming in the bloom? So enjoy the lake, including swimming most of the time, unless the blooms are like this one. And thank you for your attention.
So thanks, Ingrid, for this very Thanks, Ingrid, for this very thorough, very complete report also because we had in 2023 this very serious problem, and so I will invite the people to raise their question now. So if somebody want to, okay?
Now?
Yeah, now.
One.
Yeah. Thank you for your nice presentation. I'm wondering, do you have any experience with Voslog? This kind of, it's a kind of
I'd like to
meat, which is
that will be the next presentation. That's not my expertise. Okay.
Mhm.
I don't have any experience with it. We did not use it in Berlin in this situation, but Mike and Maìra know a lot about this and will address it.
Okay, sorry. Thank for your very, very interesting speech or narration. And I have a question. Which is your opinion about ultrasonic control algae? Control algae for water, or and if is useful for Serraia lakes?
Mike, do you want to answer right away or later?
I can answer.
Are you?
Yeah, yes, please.
One moment.
Before Mike answers, please don't ask me about these internal measures. It's really not my area of expertise, and it's the next talk.
Ultrasound is heavily promoted, but we do have certain laws of physics in this universe. So the claim that you can bring gas vesicles of cyanobacteria into resonance with the frequencies emitted from this low frequency ultrasound, well, you cannot. So from the theory, we do not find any reason to believe it works. But then, of course, these things are being installed everywhere, and we have by now enough independent monitoring to say it doesn't work. And as a scientist, I should be very careful saying things don't work. So maybe in a parallel universe on the planet Ultrasonica may work, but not on Earth. So I would put my money somewhere else. But you're of course free to do whatever you want with ultrasound, but I would put my money somewhere else.
Thanks, Mike. So this is also one, thanks Maurizio, this is an important question, no? Because there are a lot of commercial solutions which are highly promoted with very nice brochure and a lot of advertising and seller, and this very often leads only to provisional result at the time of application, but has no reason to work. There is not a biological mechanism behind it, which is giving hope that it could work. And therefore also was the reason of this day to try to speak with people who have a long-term scientific experience validated by publication. I have also a question for Ingrid. You spoke about toxicity in respect of humans, but our concern, for example, the liver toxicity is also for fishes and for in general wild animals, no? The ducks, for example, which are eating the scum or eating the fishes. So how high is the risk for water pollution by microcystin in a lake? No, this can last 1 or 2 months.
There are a lot of cases in the international literature of farm animals dying when they drink water with scum, and pets and wild animals, but not for fish and ducks, and we do not know why. But maybe they just don't swallow that much. And also, you really need to differentiate between acute toxicity that would be lethal or get you very sick, and chronic toxicity. Possibly there is some liver damage in ducks, but they don't live long enough to die from it. You know, they multiply, they have their babies. The population is not really badly affected, so, and there's too many ducks anyway, so we don't notice. That is one possibility, but it has not been well investigated.
So thanks. There are any other questions from the public? If If not, I think we can pass to the next presentation. Thanks again, Ingrid, for this presentation.
Thank you, Fulvio. Next presentation, we have the title Managing the Eutrophication, the Importance of System Analysis and Internal Loading. This is a very new topic for our country because these two kind of topics are not so common in Italy. And the two authors of this presentation are Miquel Lürling, who is Associate Professor of Aquatic Ecology and Water Quality Management at the University of Wageningen. It is interesting that the University of Wageningen set the topics of each author with some words. The words for Miquel are lanthanum, which is the chemical element which is the base of a new and important method to manage eutrophication. Bentonite, which is the container of lanthanum, cyanobacteria, phytoplankton, chlorophyll, and obviously the restoration of lakes. Miquel has a collaboration in all the continents. He has published more or less more than 200 papers in international journals, and he is also a member of the World Water Quality Alliance and the president of the Foundation for International Water Quality Management. In a total of 20 years of experience in aquatic ecology. And the last topic on which he has published is very interesting for us because the title of the paper is A Global Assessment of Lake Restoration in Practice. New insights and future perspectives. So exactly the topic which is important for our lake. And so I invite Miquel to begin his presentation. Thanks.
Well, thank you, Claudio, thank you, Fulvio, thank you, Comito Lagi, for having us here, for inviting us. And also many thanks for a great walking tour around the lake, which gave us a good insight. And, I'm from the Netherlands, from a country where, well, we don't have these things called mountains. We do have flowers though. We do have a lot of water, but our water mostly looks like this. So it's, I was very pleased to see the lake, but I also saw some dots in there. I'm Miquel Lürling. My cohort is Maìra Mucci, she's over there. Maìra works as staff member at our university, but also works part-time at a research company, which is Limnological Solution International. And that's very convenient, because they bridge the gap between the world of the academy and the world of practice. And so bridging between science and practice, and that's really useful. I don't own lakes, and they know where the problems are, so we can help out each other. Okay, this presentation, I'm not going to tell you what you, I'm not going to present to you the solution, because the solution does not exist. I can present something what you could do, proper diagnosis that will help you in finding the package of measures that might be useful for you. And then I will show a few cases from the Netherlands. And then we'll go to della Serraia a little bit, because you already have done a lot, and hopefully it will be inspiring and be helpful. And in between I will also give the word to Maìra, so I will not be standing here all the time by myself. Alright, let's see which button to press, this one probably. Okay, so just remember each lake is unique, and if you want to do something, you should always start with a proper diagnosis, always. And so try to find out where your water comes from the streams, runoff, groundwater. Where does your water come from? And then measure the nutrients that is in that water, so you can know how much nutrients come into your water system, in your system. also determine the nutrients that come from the sediment or that are thrown in or from other leaf litter and falling leaves, for instance. Measure these. So that will give you insight in your nutrient fluxes. Then do not forget to have an idea what's in your lake. So in my country we have a lot of shallow lakes, and the authorities would love to see clear water with plants, but many of our lakes have way too many carp and bream to ever get clear water. And so if you have 1,000 kilograms or maybe 1,500 kilograms of carp per hectare, it's a lot. You will never get clear water. They will always stir up the sediment. And so you need to do something about that as well. And then important, what's the lake being used for? So is it a drinking water reservoir? Is it recreational purposes? And this is important because it helps you also in your cost-benefit analysis. This is your diagnosis, and that will guide you to what we call a package of measures. And this is plural, already indicating that often you need to do more than one thing. So what do you need to do? Well, first of all, in your toolbox, there should actually only be measures that are effective. So no ultrasound, no magic solutions, regardless the fantastic claims that are being made, because all of them, if they are too good to be true, well, they are too good to be true. So that's a waste of money, don't do that. Then measures should be affordable. You can go up, and I see a lot of scientific publications with fantastic materials, huge phosphate binding capacity, but if you look how you need to manufacture this, impossible. It will be way too expensive. We can go into the hundreds of millions to treat it. It should also be feasible and easy to apply. It should be possible. Sometimes certain things are not possible. So if you want to have a huge wetland and you're in the middle of a city, well, good luck, it will not work. And it should be safe, of course. You don't want to ruin your, or to create a lot of problem. So only use these things that have scientific underpinning. And if there's an emergency, well, we do have things that can work out. If you, for instance, want to organize a triathlon in the lake and suddenly you have a bloom, you can do something, and you can use parasites to kill the cyanobacteria, and you can also flock, coagulate them, sink biomass to the deeper part. So these emergency tools are there, but they will not solve and not the issue for a long time. It's only very temporary relief. Okay, let's go to some Dutch examples from the Netherlands. I will start with a small diving lake recreational site in the south of the country, called Wageningen. Then we move to Grootmeranen, and then we go to a larger system, an urban lake in the city of Rotterdam. Okay, example one. Lake Wageningen. Small lake, sand excavation, 15 meters deep, and it started to develop cyanobacterial blooms. It was dug in 1967, and so after about 40 years, 33 years, started to develop blooms. And then usually it was planktons pubescens, and then later on you got Dolichospermum and mostly Microcystis in summer. Accumulating into 4 months closing in 2007. The caretaker of the lake thought, well, there are no macrophytes in the lake, and it used to be full of it. And there were no macrophytes, but the authorities introduced grass carp to get rid of the plants, because the swimmers complained, too many plants, I can't swim. The grass carp did fantastic. These guys here. Just to give you an idea, if you have such a 10 kilogram grass carp, can easily eat 100% of his body weight in summer per day. And these are about 60 crops of lettuce per day. And they're not efficient in digesting. So the fish was removed. Some of the grass carp had died naturally, and other fish were removed. And the banks were restored, protection from erosion, and even some bamboo and planting, but the macrophytes did not return and the cyanobacteria remained. Then it came to us and we said, well, maybe we should have a look at where the nutrients come from in your system. And
what's going on. So it's an isolated lake, very simple, no inflow, no direct inflow through streams, but through groundwater and precipitation. So that's, from a water balance point of view, rather easy, although groundwater is quite difficult. And then phosphorus was determined in all kinds of possible sources. So what's in the precipitation, what's in the groundwater, what's from the leaf litter. The swimmers, all the swimmers, they do not always go to the bathroom if they need to. And they can also stay in the lake, birds, and from the sediment. And from all this analysis, it turned out that this black part here, that's from the sediment, was by far the largest pool. So we said, okay, we cannot seal off the groundwater. It's a swimming lake, so we cannot keep the swimmers out if we want them. Leave it, well, we can do something about it. So some shrubs were pruned and trees removed, water birds, difficult to do, precipitation body, out of control. So it's difficult to do something about this, so that became options to do something about the sediment. Well, dredging was by far too expensive. So for this lake, about 600,000 euros for dredging. Sand capping, a lot for transport of sand, at least as expensive as dredging. And iron chloride, well, no, because deep down there was an oxide that wouldn't work. For aluminium, the water authority said, well, you would never get a permit for it. And then we had one remaining, and that's phosphor. That remained. And we had done some tests by then already with that. So our idea was to add phosphor in winter, but you have to go to a whole circuit and then whole trajectory of getting the permits. Took a bit longer. So and when it was April, it was already, the lake looked like this. So a bloom had already developed. Phosphor will not remove phosphate from, and will not settle it. It's a phosphate binder. It only binds phosphate. Actually, the lanthanum in it binds phosphate. So if it's in the cells, well, bad luck, because you cannot get it. So we started to add polyaluminium chloride to it, which is a coagulant, and you flock together the cells. So it's visualized here. So you glue them together. But these cyanobacteria can come to the surface, and if you make larger flux, it goes faster. So we added a little bit of the phosphor as a ballast to sink them down. So here you can see the top and bottom, so you can really sink them down. That's what we did in the lake. So, visualized like it. At the bloom, we added a little bit of the phosphor in April 2008. Then the polyaluminium chloride. Because monoxide is for cosmetic buffering, I would say it was not needed. And then more phosphor was added afterwards to do sediment capping. So, our cyanobacteria, they were really effectively flocked together and precipitate out of the water column. This was before, this was after 2 days, and then after a month. Nice and clear water. And we had in summer exactly this going to 10 meters, which is exceptional for the Netherlands. Look at total phosphorus concentrations. This is over water depth. This is over the years. This is when we did this combined flocculation and sedimentation, phosphor, polyaluminium chloride and phosphor application here. So we stripped everything and we kept the internal release low. So for several years, total phosphorus concentration was very low. But there's still an external input, so over time you will see it becomes more greener. Until today, the lake is still without cyanobacterial blooms, but it's getting gradually more eutrophic. So we calculated that this would last for 10, maybe 15 years. Well, we're now in year 18, so we're a little bit off, but you guys should do a reapplication because it's not an isolated system. And this is an external load that you cannot control. You cannot control groundwater, you cannot control water birds. And so you should remember that lakes are not isolated from their environment. They tend to accumulate nutrients. And in certain parts of the world, like in the Netherlands, it's more than it's probably here. So maintenance is needed, repeating attention is needed. That is just. And the title was also happy when it's maybe I can briefly address this one. So what we did, we also mimicked the experiment in the lab, what we did in the field. This is just to this is phosphate concentration in sediment cores that we kept in the lab. This is 640 days. So in the control, in polyamine chloride, which is very low dose, you have high phosphate concentrations. And in the phosphate treatments, even after 2 years, it's very low. This is also what you expect, because the lantern precipitates with phosphate. So it keeps it down. In the field, after some years, you see black internal load starting again, because of the ongoing external load. And that means repeated interventions are needed. So, this application, 50,000 euros, 17 years, more than 3,000 euros in the season. Who has a swimming pool? Somebody here owns a swimming pool? No? This is a swimming lake and a diving lake. No? People who own a swimming pool know that you do maintenance on it. If this is an official swimming site, the grass, the beach is being cleaned and maintained regularly. The grass around is mown and the bushes are pruned. This is a multifold of 3,000 euros. So the authorities there spend 35,000, 50,000 euros to maintain the site. But they do not allocate a little bit of money, a few thousand euros a year, to maintain the water. To me that's a bit weird, but that's apparently how it works. Okay, example number 2. Another lake in the Netherlands called Maìra. The authorities wanted to get rid of cyanobacterial plumes, like this, or from above, like this. It's not a very big lake, some fish in there, no plants, 2 streams came in, drainage system, and a small stream. And sometimes some fish died. A water balance here was made. So different groundwater well, and this inflow, outflow was made. And a lot of potential phosphorus sources were also measured in the meantime. So again, this is a whole year of monitoring. We already very rapidly saw these streams bringing in quite some nutrients. So we asked the hydrologists, what about the diversion around the lake? Can we do that, or will it dry up? And they said, well, no, you can really do this because there's sufficient groundwater inflow and also sufficient precipitation, so your lake will not dry up. And they were right. The only thing you see is a higher amplitude in the water level fluctuation. That's it. So we could do that. And we had to do it because our system analysis gave inflow as a reasonable large source, runoff from the land, and then we have leaf litter and birds here, and this is the internal loading. It was decided to target both external and internal. These red lines are simply to indicate the loads in which we can expect a shift in the lake. We use a model for that, so there are some uncertainties in it. But we need to be at least between here. So we need to be below this one. If you're above this one, your lake will never clear up. It will always go back to a turbid lake. So that's why it's important to have insight in the nutrient load of the lake. This is for shallow lakes. There are different models for deep lakes. So we need to have an idea. And here we had to remove both. So what was done? First of all, fish removal. Then the entire lake was dredged. The dredging, the sand was separated from the silt. The sand was used for construction. The silt was used in agriculture because it was not very polluted. It was nutrient rich, but there was no industry around it, so no metals, no pesticides. So that's a good thing. So that could be done. Then the banks, mostly were hard, they were softened, so reconstructed. The streams were diverted. Because of the dredging, organic rich material was exposed, peat. And if that oxidizes, you get a lot of nutrients, so it has to be capped. So a layer of sand was put, about 30 centimeters, was put on the sediment, and in it was a little bit of phosphate as an active barrier to cap phosphate. The water column was stripped of particles and of phosphate. Then school kids helped out in planting magnified, because if you dredge, you remove also the seed bank, so we added plants. And we had to do some additional fish removal. So a whole bunch of things. And this is the result. Total phosphorus, this is the nice annual oscillation. So every peak in summer, this comes from the sediment. This is what you see here. This is the period of intervention, and this is total phosphorus afterwards. And actually continues until now. Because of this external load reduction and sediment removal, this happens to total margin also goes down. Chlorophyll, large peaks before. This one filamentous green algal peak here. And cyanobacteria, no major blooms, but they are not gone. And so once in a while you see a little bit of cyanobacteria there. But the major blooms did not happen. So if you look at the averages over the different periods, and it's a strong reduction down all planting helped. There were a few duckweeds in 2014, 2015. No, there were no plants before, so planting really helped and started to expand. And these guys we didn't want to have in there. No carp and no bream, so they had to be removed repeatedly. And in the end, the fish stock is more or less there where the authorities agreed it would be. For me, it's still too high, but that's another discussion. So, if we have derived also for small water bodies in the Netherlands, derived also targets for the water framing directive, so if I plot them here, in red is bad, and in orange that's insufficient, in yellow it's moderate, and green that's good. So this is summer chlorophyll and total phosphorus. Then it was moved from bad into the region of moderate and good. So this is an example where combined measures, if you are in this region, can help to get clear water and also to stay there for a while. Now we go to a larger lake, 1 square kilometer. It gets 3.5 million visitors per year. It has blooms since the late 90s, and in 2009, 2010 it was dredged and sand capping was undertaken. And banks were reconstructed, and it was using sand and woods, and the nice YouTube videos about that. However, something went wrong there. And the material used for reconstruction came from canals. It was not good control by the authorities on it. And the year after, there was a massive outbreak of Eutrophication, and later by Protozoam and microcystis. This actually is the Eutrophication bloom you see here. That gave quite some political benefit, because this, so if you're going to dredge and do sand capping in a 1 square kilometer lake, well, we talk about more than 20 million euros. Yeah? Down the drain. Not entirely, but it was not working out as hoped. Well, hydrogen wasn't prioritised there. I will not go into it. But in the end, in 2019 there was a plan for sand capping again. But the external payload was way too our consultancy defended Bos decided it's way too high. And there was periodic high internal P release from high pH because there were plants in there causing high pH. They also have high pH in the lake once in a while. And there was also something with the peroxide with it. So for this lake, well, lanthanum modified bentonite. It was phosphorated, was tested on the aerobic conditions, anaerobic conditions, and then at different pHs. So different pH. If it's aerobic and you increase the pH, you will get alkaline desorption. That's what you see. If it is aerobic, and usually at low pH, your phosphate will stay in the sediment. But here, at higher pH, it really comes out. And with Foslock, it stays in. And that was also tested in enclosures in the lake. So this is total phosphorus in the Foslock treatment, and this is in the control, and the lake is installed there. There's total phosphorus and chlorophyll. Chlorophyll is very low in the phosphorus enclosures and increasing in the control. So from this it was concluded that well, the lanthanum modified bentonite keeps the phosphate in the sediment and it seems fit for purpose in this lake. This was not the only thing that was done. Inlet, nutrient-rich inlet was diverted. The sluice gate was modified. It used water from a nutrient-rich river. Now it's reversed, it uses water from the lake, if operated properly. Sluice overflows have been dismantled, actually they're not existing anymore. Leaf litters are being removed. Also bird dropping, so there are people walking around with these vacuum cleaners, and they just suck up bird droppings on the pavements, etc. near the lake. Deforestation of inlet water has not happened yet. It was supposed to be done, and now it's 2027, 26, right? Yes, they should do it. Because the current iron chloride dosing is not efficient. It only reduces about 50%. It's not efficient enough, so it should improve it. And then in November 2021, 1,000 tons of phosphate was introduced in the lake, as you can see here from Waters. For this lake as well, the authorities budgeted money for maintenance and for repeat intervention because they know it's not isolated. It will connect and accumulate phosphates. I do not need to go there. This is an experiment. We always do experiment. We mimic the application in the lab. I will show you the monitoring results, phosphate concentrations. Before, this is the phosphorus application. This is after, total phosphorus, before and after. So you can reduce phosphate. You can really chemically mobilize it. You can chemically mobilize it, and you can reduce the big cyan blooms, and you can immobilize and keep it also down at high pH. That's what and we know that. We know from all the experiments we did, and it also works out in the field, so it's nice to have this confirmation. To sum up this part again, each lake is unique. You can see this also here, different shapes, different colors. So, do this diagnosis, look at the water and nutrient fluxes, what is in the system and the function of it. And then probably you need to do catchment measures and most likely also something in your lake. Okay? Unless you have a lot of time. But in my country, diffuse nutrient load is the main issue. And the soils, well, maybe you're aware that the Netherlands has a massive agricultural industry already for decades. If we would stop with that, the diffuse load will continue for decades, or maybe centuries. So it will not solve the problem. And we have a lot of nutrients in the sediments that are not leached out that easily. And so you will not have a quick improvement of many of the lakes. So to conclude, do not copy-paste measures. Always start with system analysis, and probably need to do more than one thing. The Lake Serraia intervention was successful. Price €2 million. Lake Houtmaken was successful. €50,000. But that's only the application. So all the research we did there, you may multiply this by 6. Lake Serraia Plus, successful, €15 million. So you have an idea what it costs for screwing up our lakes. That's the price you have to pay if you want to restore it, and you're not done with that because you need to maintain it. So this is always better. Prevention is always better. This is your lake. Yesterday I saw something bubbling in there, and today I saw that it is. It's not something you would like to see in such a lake. And I noticed that already. A lot of studies have been done. A lot of information is there. But it's first of all, it's in Italian, so it's a bit more difficult for me to decipher what has been done. But I also think it could have been aligned more better. So it misses certain aspects of it. And I will give the word to you, so you can continue with that.
Thanks. Yeah. So, okay.
To present the next author is Maìra Mucci. Maìra Mucci has a doctorate in the same topic, working with Miquel. And it is interesting to note that if one looks at specific words on the page of Wageningen, we need 2 new words, apart of the previous one, typical of Miquel, who are dredging and macrophyte. So, new topics. But what is interesting for us is that the last paper of written by Maìra is combined measure in lake restoration. So, a multifactorial approach to the problem. And this is probably the main point which Maìra will discuss with us, or not? Please.
Thank you. Yeah. So, as was already mentioned by Ingrid and Mike, today we had the opportunity to walk around the lake. Thanks also for the Comitato for organizing that. And we also received a lot of reports about the lake. So as a scientist, it's always very nice to see that people are looking at the problem and doing a study on it. But we also identify a few gaps from the research done so far. There is a lot of uncertainties and also gaps on our external load. So as Michael mentioned, it's important to know where it's coming from, the problem. And of course, when you have uncertainty, then the solution becomes also uncertain. So we see it, for instance, I think the activity with animals, or I'm not sure if it's specifically horse, but you are have a better Italian than mine. It comes from 65 to 1,000 kilograms per year. So if you look at in the range, the smaller range, that's something that might not be that important. But if it's the larger range, then it's something that needs to be targeted. So when we have a more precise idea where the problems come from, then we can really target precise the source. So that's something that we spot on it, and it would be nice to improve. Another very important one that we saw as a gap, it was the sediment, but also the groundwater. So you have an idea how much it enters, but we don't know nutrient-wise. So we have amount of water, but not of nutrients. So, and if the problem is nutrient, then we really need to know how much is entering. And also the sediment, right? So it was already, I think, mentioned in one of the reports that there was no research on sediment done recently. And I think the same report mentioned that was research done, but they only analyze total phosphorus in the sediment, which is nice, but does not give us an idea how much of this phosphorus is coming from the sediment to the water column. So we don't know how much actually it's available for the algae to overgrowth. And the sediment was already highlighted by some example that Michael gave, and also Ingrid. It's a very important component of the aquatic system. So everything that enters in the lake, if it's not processed in the water column and not flushed out of the lake, it will accumulate in the sediment. So imagine over several years, decades, centuries, everything or almost everything has higher chance to be accumulated in the sediment. And there are several methods that we can use to have an idea of how much the sediment can contribute to the system. There's like modeling approach, but our preferred approach would be actually sampling the sediment. And we do that by using intact sediment core sampler. So a lot of people use like a grabber that meets the layers of the sediment. But if we don't separate the layers, we don't know which one actually is in contact with the water column. So that's very important to know. If only 10 centimeters is in contact with the water column or 20. And we can only know that by analyzing the sediment. So you can imagine if you have a sediment with a lot of water, low density, it's very like waterish. So it will really be mixed with the water column. But if you have sand, that will not be much reduced. But also we need to look at fish. So you can imagine that fish swims next to the sediment, it will really resuspend. And some fish does it, like carp, brim, others they do not. So it's important to check the sediment, but also the biological community, as Michael mentioned, to have a whole understanding of what is going on in the system. And when we slice this sediment, then we can check for certain compounds like phosphorus, but we also do actually what we call a sequential phosphorus extraction. So we take these layers, we bring to the lab, and we exposure the sediment with different chemicals that will mimic the what's happening in the lake. So we exposure to a chemical that will mimic anoxic events. So we know how much of nutrients come from the sediment to the water column if the lake turns anoxic. Also with high pH, that's also observed in Lake Serraia. So then we know precisely how much will be released. And also over time, bacteria will mineralize the organic phosphorus and then would also be released to the water column. So by doing this analysis, we really know which fractions phosphorus is bound to and what happens in the lake, how much will be released. So in the graph there, we can see different phosphorus fraction. So the purple one, that's the residual fraction. Is that the one that is bound so strong to certain compounds that will not be released to the water column. So it's a fraction that we don't need to worry about it, which is good. But if you only analyze total phosphorus, then you don't have this insight of the different fractions. And together with this analysis, normally we also do it other compounds like iron and sulfur. And this will give insight on the possibly effectiveness of certain measures. So if you don't have enough iron, aeration might not be actually a good approach, because even if there's oxygen, there is not enough iron to bind the phosphate in your sediment. So this gives us a bit of insight of the chemistry in the sediment. And this, normally we also do it sampling different locations in the lake. So you can imagine that the shallow area in Lake Serraia, the sediment will be very different from a deep area. So by doing this analysis like in different locations, so here I bring Kralins Plus as an example, that the lake that Michael talked a bit about before. There we took a lot, that's not needed to be honest, but we took at 420 sediment cores and we sliced them, analyzed it, and we could actually identify hotspots of phosphorus release. So you can really target locations where it's needed. That's an approach that can be done with those analyses. And then I would like also to repeat what Fulvio mentioned at the beginning of the symposium, Ingrid mentioned, and Michael mentioned. But from my experience, it's always good to repeat this. So each lake is unique. Although they look similar, they can really be like behavior different. And we can think the lake as like a human as well. It's very complex. And if I have a fever, I would like to know the cause of it, right? And in the lake, if they have a problem, it's important to know the cause of it. And if I have a fever, I would maybe drink more water, take maybe antibiotics, rest. It's different measures that will do it. And the lake's as complex as us, or even more to be honest. So we really need a lot of measures to solve the issue. So based on that, we really cannot just copy and paste, because it works in one lake, it will work here. That's not truth. So we really need to start with a system analysis. And you do have a lot of information already from all the reports. So it would be good to review everything and try to see, okay, what we know, where we need to put our efforts on it, so we can really direct the efforts to find gaps and then do the research on those gaps. Then it's important to construct like a management plan, also based, okay, if this measure would work, how much it would cost, how much to reduce the phosphates. We can really actually balance all the measures possible. And probably that you needed not only one solution, but like a combined solution. And with that, I would like to thank your attention and also invite you to join our community of practice. So we have a project that the idea is to get everyone involved on lake restoration and sustainable use of phosphorus. Not only scientists, not only government, but also like communities that, like the Comitat, that really get together to discuss something that's highly important. So please, if you would join us, it would be a pleasure to share your knowledge and also ours. Thank you very much.
Okay, thank you to Miquel and Maìra for the very nice presentation. I have appreciated very much the fact that Miquel showed the general criteria of the approach and some important examples, but also that Maìra proposed to us some application to our case. So this is extremely interesting, I believe, not only for the scientists, but also for the politicians and for the administration. So thank you very much to you. Are there questions in the public?
Good evening, but my English is not so good, so I prefer speaking Italian. Complimenti chiaramente ai relatori e al Comitato Laghi per tutto il lavoro che sta facendo e per tutta la visione alternativa del problema lago che c'è. E per quanto riguarda le piccole bolle che ha visto andando verso il lido questa mattina, in prossimità di quella boa arancio, sono legate all'autorizzazione alla messa in funzione dell'ossigenatore del lago. È in fase di messa a punto, quindi è sovraossigenazione dell'acqua entrando e quindi sta scaricando un eccesso di ossigeno. Non c'è nessun tipo di problema, non è nessun tipo di inquinamento. Mi piace molto l'approccio del verifichiamo i dati prima di prendere delle decisioni. Sono dati datati 2007, pre-Baia, quindi con un flusso di ingresso totalmente diverso dall'attuale, con un'analisi di sedimenti da approfondire e sicuramente darà degli sviluppi, quindi i primi passi per trovare una soluzione, chiaramente non definitiva, che non andrà manutenzionata, e complimenti ancora.
Please, Ingrid, may you answer to this?
I couldn't quite understand the question.
he gave an explanation of the bubbles we have seen, indicated in your presentation we have seen this morning, and also his compliments for the proposal you made. For the general proposal.
Explanation for the bubbles that we saw.
The bubbles we have seen this morning.
But I think that's more a question to you, no?
I thank you very much. Thank you. Yeah. I didn't hear question mark.
I wrote a question mark. I would also have a couple of questions for this case for Maìra or Mike. One is Serraia Lake every summer, according to the official data of the Environmental Agency, as a pH that during the bloom is going to value to pH 9.2, 9.3 or higher. The record was in 2017, I think 10. So how much it is would change the release of phosphorus from the bottom? The second question is complementary. Since, okay, I understand it's very interesting the idea that we should do a map of the hotspot of phosphorus. Makes sense also because in Serraia Lake we have one part which is under the mountain where we can roll out the idea of external pollution, while another is the anthropic side. So most probably there are huge differences. But one treatment with phosphorus could be done mainly in the shallow lake. So Serraia has 45 hectares, of which 8 hectares are below 4 meters so there is a poor stratification or no stratification, and they are close to the probably also the most polluted. Just to know if it would make sense that phosphorus is applied only when the lake is more shallow and not where it is 10 or 12 meters, or should be done everywhere.
Okay, thanks Fulvio for your nice questions. The high pH. I'll do it like this because there was an echo. This high pH, well, we get this phenomenon of alkaline desorption. So also it depends on where it has been measured. So if you only measure the pH just on top of the scum, and if you go underneath near the soil, the sediment, and it's pH 8, and nothing bad, but if it's the entire water column, then all phosphate absorbed to metal oxides will be released, extracted. Actually, that's also what we conveniently use in our sequential extraction method. We use sodium hydroxide to get metal oxide absorbed phosphate free. That's also what happens in the lake. So high pH will, you can oxygenate whatever you want, but if you have a high pH, it will take the phosphate out of the sediment. So that will happen, and that will fuel the blues. For the second question, a lanthanum-based product can be used in the shallow lake, but also in deep lakes. In deep lakes, it would, and in larger lake, it would make sense, as done in a large shallow lake, to search for the hotspot, because you can more directly target there. Otherwise, you're spreading out and you're actually overdosing in certain sites. That would be a waste of money. So, hotspot identification for a larger system is recommended. And usually in deep lakes, most of the problem occurs deep down. And so, but it's good to have an idea what is your internal load. At this moment you don't know. You don't even know if it's a real problem. Yeah. So this is something you should find out first.
Could I add? To add the experience from Berlin with the role of the phosphorus from the sediments, in Lake Tegel, we did the sequential extraction, but quite late in the whole process, after the first 10 years of restoration already. And we found that the fraction of this redox sensitively bound phosphorus was actually quite low. So it wasn't that much of a problem. And with a water exchange rate of several times per year, it's been being gradually diluted out of the lake. And at Schlachtensee, there was more redox sensitively bound phosphorus, but because the mineralization of fresh organic matter is so much less, because there's so much less algal blooms that sediment organic matter to the sediment, you can really see now that the sediment is no longer this black, yucky, floppy stuff, but you go in and your feet stay clean. Yeah, it really, after 20 years, it got oxidized without any treatment. So we just have a very small area of the lake now where it's still anoxic. We can see that there's much more oxygen. In the old days, while it was eutrophic, it started being anoxic below 4 meters, and now it's anoxic only below 6.5 meters. So it actually improved without needing any treatment, and possibly if we would have had this analysis in the beginning, we could have understood that. This way it was just lucky.
Are there other questions?
A question, please. How important do you think is having a high resolution bathymetry of the lake? Because we lack this information. We have only some large scale bathymetry, but not laser beams or something like. Is it worth to spend money and get a very accurate bathymetry? Thanks.
Yes, always a good idea. And if you do it properly, you will also have an idea about the thickness of the sediment layer. Because you're using the sonar to do so. So, yes. And usually the pattern of the lake is not what people think it is. So it can be, in this area, it can also be very erratic.
Yes. Thank you.
Thank you for your presentation. A practical question. How did you manage to remove the grass carps? You told in one example that you removed not only fish, but especially the grass carps.
Usually we hire professional fishermen to catch the fish. In this lake, most of them died already because of age, and others were caught, and the last part was harpooned out by divers. But I didn't say that.
Yeah, really, yeah.
Are there other questions? I have a last one for Miquel and Maìra. To complete the description of our system, to apply the system analysis you are claiming for, what do you believe we need absolutely and we don't have at the moment? What is the kind of data we do possess and we must absolutely obtain?
I guess now the sediment, that would be something that's a big question mark, because the external load, you do have a wide range, although a lot of uncertainties, but yeah. Yeah, then that would be nice to have it a more certain data, maybe 1 year round, not only flow, how much is entering the water, but concentration of nutrients, okay, how much is actually entering, and the sediment, that's something that maybe for now that's a question mark, and if we analyze and it's nothing, that's a win, right? So then you can really focus on what it matters.
And from the discussions we had while walking around the lake and talking in different small groups, my impression was that it's worthwhile to spend the next 2 years on doing the research to fill the gaps and taking some time to also look at the data and discuss them. And it's probably more than 1 year because you always need some time to really mentally process everything and discuss it. So it's probably the best way to spend the money you have to first tell people we need 2 years to come up with a good plan.
Miquel, are there examples of a combination, multifactorial combination of fetal depredation and lanthanum method? Are there in the literature effective combination of these two kind of approach?
Yeah, well, phytoremediation is a broad term, so also this introduction of macrophytes would cover that. And the answer is yes. And you even have a case here in close by in Bolton. Do you know the name of the lake? So it was treated with an anti-modified clay, and afterwards macrophytes were planted to help to improve the lake. The same procedure has been done in an Austrian lake, at the Eutrophication, several years ago. So in our case, quite a few, well, the example set for Grote-Manare, the shoreline was also completely reconstructed, helophytes were planted, so you can, and macrophytes introduced, so that's also a kind of phytoremediation. It depends, of course, on the size you have available, but you could easily do this with the wetland, and you can even improve the binding capacity if needed for a wetland to introduce some of these lanthanum products to get even more phosphate retention, also in periods when the plants will grow. So there are a lot of possibilities there, but it really is case specific. That's the power of combining measures.
Okay, thanks for suggestion on Miguel. If there is no other question, I may pass the voice to the President.
I just want to thank you again, Ingrid, Maìra, and Miquel, for the impressive amount of information you decided to share with us. I think that we have a lot of information that we have transfer to the people who have to take decision. So, quello che voglio dire è che noi non vogliamo sostituirci a chi deve poi intervenire. L'obiettivo di questa conferenza è quella di raccogliere informazioni e di stimolare gli organismi che devono decidere, le amministrazioni, ma soprattutto i tecnici che devono supportare poi l'amministrazione, a prendere delle decisioni e guardare oltre. Le informazioni che ci hanno dato sono veramente anche molto aggiornate, no? Vengono dall'esperienza quotidiana che loro stanno facendo costantemente, quindi credo che sia stato un ottimo momento per avere un aggiornamento e uno stimolo per anche chi poi deve intervenire. Noi domani ci sarà una riunione organizzata dal sindaco con gli organismi che sono deputati poi a prendere delle decisioni, supportare l'amministrazione negli interventi. Credo che tutte queste informazioni saranno poi riportate anche domani, e sperando che poi siano recepite e che ci sia la possibilità, la volontà di guardare oltre quello che è stato fatto. Perché il nostro lago è unico, come si è detto, come tutti i laghi, no? E quindi ha bisogno di interventi che siano specifici. Questi 30 anni sono stati raccolti dei dati, ci ha fatto sentire che ci hanno detto che non sono completi, ne servono degli altri, e credo che questo sia indispensabile per poter poi realizzare e intervenire in maniera più efficace di quanto non sia stato fatto adesso. Io veramente vi ringrazio tanto per la nutrita presenza, rinnovo l'invito a unirci a noi per il brindisi che avremo qua nella Corte, perché è un momento importante, insomma, aver ricevuto la bandiera verde da parte di Legambiente è veramente stato un momento che gratifica chi ha lavorato in questi 3 anni, e quindi è giusto festeggiarlo, e festeggiando il riconoscimento festeggiamo anche il Presidente che ha guidato in questi 3 anni il Comitato in maniera così efficace. Grazie per il tempo.